today's lecture is about spreading phenomena in networks. So we'll talk about rumor spreading, epidemics in networks, and so on. So before this lecture, you learn how to compute something on networks. So it means that you have some graph, you get it from some data set, from open set, from the web, and after that you try to compute something. And this new topic and all the rest in our course will be devoted to learning some process on networks. So it means that we have some idea what's going on the network. And for example, if we are talking about something like, for example, global contagion, we have outbreak of SARS in 2003, and it's like we have a lot of cases of this case. We have fatality rate. We have 37 countries which were engaged in this type of activity. And the model is just simulation something on network. When we visualize gray lines as a passenger flow and red symbols, it's something like epidemics location. So what about disease spread? You usually know that, for example, in Moscow during winter, we have always epidemics of flu, when everybody gets sick, and it's like it's really hard to not catch a flu and so on. So in these cases, we may say that somehow we're affected when the disease is spread. But how we're affected is based on the network structure and network formation, how disease may spread based on our social community interactions. What about this flu contagion, for example? It's like we visualize several steps or several processes of infection spread, where infected are marked as red, or friends of infected are marked as yellows. And if you could say, from the first picture, it's just very small number of persons who get infected. But next, infection spreads and covers almost all the graph on the right bottom part. So it means it's like we are really affected by our friends. So usually it's like you get infection, something like from the air. It's like you get to some place where some infected persons was. But next, the infection spread is based on our friendship relation, to which places we go, with whom we communicate, and so on. And this infection spread may really grow to the epidemics when we say that really major percentage of population got infected. This is what's called epidemics. And of course, the main idea is, for researchers is how you could prevent these epidemics. Another case is just that not only diseases could be spread. And it's like if you have a network, then, for example, friendship network or Twitter subscriber network, you could have rumor spreading as epidemics. And you have to remember what is Orange Revolution, when we happened a lot of revolutions in North Africa. There was some rumor spreading. And this was also like epidemics, because there was some information which may be not true. It was not authorized by legal authorities. But it was so relevant to all the people that it spread directly to all the network. And every people get this information. And from this starts protest meetings, and so on. So it means that in some cases, epidemics may be not only by disease, but it's just a spread of information. It may be spread of iPhones. Maybe buying new iPhones is also some kind of disease, but just in general, it's called like into shop, to make shopping, not like into buy new models of iPhones. But just in general, again, it could be modeled as a spread of epidemics, because when you see that the people around you are buying iPhones, new iPhones, then you also is affected by this as a social being, and you may be also like to buy a new iPhone. And when we are talking about mathematical model of epidemic on networks, we see that we have given a network G of potential contacts. And there are three states for this model: susceptible, infected, and recovered states. So what does it mean? Susceptible is just original state when the person could be infected. At next, when the person is infected, he then in some time could be recovered. So it means that we have three states, and from us as susceptible we go to I, infected state, if there occurs some infected person in our neighborhood, for example. And from being infected, we go to recovered state when we get some immunity to disease. And we consider probabilistic model, which refer to state of node, we say that Si of t representing probability that at time t, the node I is susceptible. Again, I index represents the node, and S, X, and R represent the state of the probability to be in the current state. Xi of t represents the probability of a vertex I to be infected in the current time step t. And Riit represents the probability that a node I is recovered at the time step t. And we have just two parameters, beta and gamma, for spread of epidemics. Parameter beta is called infection rate. It is probability to get infected on a contract in time, delta t. Well, delta t is just a discrete time. It may be different data, it may be seconds, it may be hours, it may be days, and so on. But just when you fix the discrete time model, this model could be considered as discrete time choice model. And you say that's just a probability to get infected in one small period of time. And gamma is recovery rate. It is another parameter which tries to balance our model. And we say that it is a probability to recover it in a unit time delta t. And what about network? Of course, connected components, that just means we have all nodes reachable. So we couldn't spread any kind of infection to the nodes which are not connected to the original one. Yeah? So this is just what is called quarantine. When there are really dangerous diseases, the persons are sentenced to quarantine. So it means like their contacts are being cut. And in this way, people try to stop disease spread. But inside connected components with at least one infected person, of course, all the persons potentially are reachable for infection spread. We say that network is usually considered undirected because spread of disease is something like undirected. It's a matter of knowing person. And if graph is complete, it's like we'll have full mixing model, but of course, the spread of disease is usually based on the current network interaction. Because when graph is complete, it's just we could omit the graph and say that everybody could spread the disease to everybody, but usually it's not the case. And this type of models were suggested by models of mathematical epidemiology. It was presented by Kermack and McKendrick almost 100 years ago. And there are two kinds of processes. One process is the probability of node in the middle of the star to be infected. And researchers suggest that probability of node could be computed by the following formula. First of all, we say that in order to get infected, we should be in susceptible case, or we should be able to get infected. And this is represented by multiplier Si of t. Yeah, so this component represents the probability that we are in susceptible state. After that, beta parameter gives us infection rate, so it multiplies the probability to be affected by infection rate. And after that, we ask, how will we get infected? And we say that in a small period of time, we just sum up all the probability that our neighbors are infected. So we just say that more red person, more red infected nodes in our neighborhood we have, more the probability to be infected for the current node. And what about recovery? Recovery process is a little bit different. We have a red infected person in the middle who get recovered. And we say that recovery rate is dependent only on the probability to be infected in the current step. So we say that probability to get recovered is Xi of t, so this is the probability to be infected in the current model, multiplied by gamma, which is recovery rate. So this is just very understandable and simple mathematical model. We just say that if we are susceptible to infection, then we need to aggregate all the probabilities from infection neighbors and say that we could compute the probability to be infected. And for recovery, we just say that we need to compute the current probability to be in infected state, and after that, multiply it by recovery parameter and get our probability to get recovered in the current state. So, what about different models? We say that there are three possible ways to be in the current state. It's susceptible, which is affected to infection, then to be infected, and in some cases to be recovered. But the simplest model, which is called SI model, say that there is no recovery option. So it means that every person could get from susceptible to infected. To say it in simple words, I call it zombie apocalypse, yeah? Because this is kind of disease that could not be stopped. You could not cure this disease, yeah? Because you have no recovery state in this model. You just get from susceptible to infected. And for this case, again, you have probabilities that node I is susceptible is Si of t, infected is Xi of t, and the sum of these probabilities equals 1. So this relation holds. And next, we need to model infection rate. So we say that probability on the next step to be infected is the probability to be infected from the previous step plus this formula that we talked about in the previous slide. So we say that we need to sum up probability to be susceptible in the current state. After that, multiply it by infection rate and sum all the probabilities of our neighbors that are connected to the vertex I. So all this j are taking only those that are connected to the vertex I. And this is infection equations, which are presented by differential equations. Like, even if you don't understand what is differential equations, you could just look on this formula and say that on the left part, there is a velocity, how the probability to be infected changes over time. Yeah, this is velocity of how changes are going. And on the right part, we have this formula, beta multiplied by Si of t and sum by all neighboring vertices xj of t. And in SI model, when you try to simulate this type of models, you have every node at any time step is in one state. It's just susceptible or infected. And when you try to simulate these types, you just initialize C nodes in state I. Yeah, so it's like we initialize some number of infected persons. There are some zombies starting to make riot somewhere. And each time step, each I node has a probability beta to infect the nearest neighbors. So we have this process that if we get infected and he is connected to some susceptible, then with probability beta, we have something like tossing the coins and trying to understand whether he will be infected or not. And from having some infected and susceptible persons, we have infected persons. The current step, it's like on each step, we could increase twice number of infected persons and even more. And let us show for different beta parameters how the infection could spread on Zachary Karate Club. When we take beta as just 1/2, we start with 2 nodes that got infected, and after that we have infection spread. So as you see, when infection spreads into vertex with high degree, from that moment we have large outbreak of this disease. And when it gets further, we have only zombies left, yeah? So it will be karate zombies. What about graphics? How the population of susceptible and infected persons changes over time? We have increase of number of infected persons. Because every time new infected persons could have more non-infected persons, more susceptible neighbors, and they will be infected. And of course, number of susceptible persons decrease to 0 over time. So this is case where you have no optimal solutions to overcome disease. And if you talk about the growth rate of infection, it depends on maximal eigenvalue of adjacency matrix. And all nodes in connected components get infected when time tends to plus infinity. So it means that probability of a vertex to be infected tends to 1. So it's like we'll almost sure have all the nodes in the graph to be infected when t tends to plus infinity. Next, we have SIS model. SIS model is a kind of model when you get from susceptible to infected state, and then from infected state, you could return to susceptible state. It's not so hard disease, but it may constantly go on. Yeah? And if I'm talking again about something like spreading of rumors, SI model may be something like, you may say that you were previously in one state of mind. For example, you were thinking about, I don't know, you are thinking about that Earth is the center of universe, and after that there is a spread of knowledge that there is a sun and Earth is rotating around the sun, and next you got infected by new knowledge and you accept it, and everybody accepts this type of things, except some group of guys who still think that Earth is a plate thing. Do you know about these meetings? There are really a group of people who think that Earth is flat circle, and they even have their own conference and so on. I can say that I wonder what's really going on there, because it's really fun to be in such events. But for these cases, I will present just another example. So what is about going to be infected in a constant manner? For me, in particular, it's just watching every time on the course of ruble, dollar, and euro. Because previously I was so skeptical. I was just thinking that ruble is okay and having my storage and earnings in ruble is okay. But after that we get crisis, yeah? When dollar increases twice. Yeah, it was 33, now it is 65. And now every week when I try to type into Google search bar, for example, I see some news which are top 5 queries. And among them there is kurs rubля, yeah? Course of ruble. And I get infected because I want to know what's going on. Maybe another problem happens, yeah? And really with some periodicity of 1 week to 1 month, I got infected by this news. I decided to watch these charts to think maybe I should get my money to dollars, to euro, and so on. This is panicking. And after that, I see nothing serious is going on. And I got back to my skeptical case when I'm storing in rubles. Yeah? But this is a process that really, it happens every time. And you could not stop this gradually because you will be always worrying about your earnings. And in this case, when we are trying about just modeling about epidemics, yeah, it's such kind of disease which happens annually, but you could get susceptible and without any kind of immunity. So you could catch a cold usually, yeah? So you catch a cold, after that you get healthy, but in the next case you got hot, some wind blow, and you get another cold. And when you try to model this, again, every node has just 2 states. Again, it is S and I. And we initialize some nodes with the state I, so we initialize some infected nodes. After that, each node stays infected for 1 over gamma time steps. So this is discrete choice model when we say that we specify how long the infected node remains. After that, it got again susceptible, so it got healthy. And on each time step, each infected node has a probability beta to infect its nearest neighbors, so to infect its direct neighbors. And after this tau of gamma time steps, node recovers. So we have 2 types of process. Infected plus susceptible get us new infected nodes. And from infected nodes, we have recovery and recovered nodes. What about examples? So again, choose the same beta equals 0.5 and tau equals 2. So it means that for 2 time steps, infected nodes remains infected. So, have you seen that the original 2 nodes, which are red here, in 2 time steps became again susceptible, so they overcome disease. And next, they again got infected. Yeah? See vertices 6 and 7 in the bottom. And when you try to watch on this type of things, still going on, and so on. So, infection was not overcome over time. It somehow stabilized. So if you see on the plots, at first position, the number of infected persons increases, after that decreases, after that a little bit increases, and so on. But in the end, it's something stabilizes. So it means that it's like there will be everybody, some persons who are concerning regarding the course of ruble. There will be a lot of persons and some stable number of persons who got sick over time. It may be different persons, but if we just count the population of this person, then we may have this stable process of number of infected persons. Let us choose another process when we decrease infection rate. When we decrease infection rate, it means that the spread of infection is much slower. And the result of this epidemic spread is just that everybody got infected and got susceptible after being infected. So it's like many of the vertices even don't have a chance to be infected because infected persons were not reachable. And now all the infected persons removed from this network. So it means that spread of disease finished. And this is a good position for this type of things. And if we plot charts on this case, number of infected persons just decreases to 0. And so epidemics start. No epidemics, no disease spread, and so on. And just few persons got sick, and after that they cured, and no further spread was made. This is SIS model. And SIS model is highly affected by the following coefficient of 0, which is called threshold for epidemics. And in fact, this threshold is equal to 1 over maximal eigenvalue of adjacency matrix. But what you have to know is that there is some constant for which you should compare beta over gamma. So you should take infection rate divided by recovery rate. And if it was simple case when no graph was chosen, then you should compare it with 1. And for example, if it was less than 1, then infection is less than recovery, and everybody will get recovered. As it was plotted here, the just number of infected persons tends to 0. But if we have a graph, then instead of 1, we'll have specific coefficient which depends on adjacency matrix. And if beta over gamma is less than this coefficient, then infection dies over time. So it means that we have some people gotten infected, but their population decreases over time, and in the end, we have almost no persons who get infected. But if beta over gamma greater than this threshold, then infection survives over time and becomes epidemic. It may be not 100% of population that got infected, but some stable one who will be constantly infecting the others. So in this case, you have just only two options. Either you have infection death or infection stable surveillance. Next, we go to the third model that you have to know, and you will be applying this model in your homeworks. And this is, I can say, the most appropriate model for modeling real disease, when you have something like when you get infected, and after that you get recovered. And by recovering, you obtain immunity to this disease. So it means the next steps, you will not get infected by the same disease. Usually when we say that some childhood diseases that you could have this disease only one time in your life. And for example, it's not, in some cases it's just that you could have this disease only once in your life. And in this model, after you get infected, you will be recovered in some time. So we have three states, SIR, and the same as the model. S is susceptible, then susceptible get infected, and infected get recovered. We initialize nodes in state of infected, so it's some kind of initially infected persons. After that, we have the same tau of gamma, which equals 1 over gamma time steps. It's just a number of time periods in which node stays infected. And on each time step, each node which got infected has a probability beta to infect nearest neighbors. And after that, after tau of gamma time steps, node recovers. So we have this process that I goes to recovered nodes. And recovered nodes do not participate in further infection propagation. So it means that if person is recovered, it doesn't spread the disease further. It's not always true for all the diseases, because in some cases you may have immunity to this disease but still be a spreading person. But in this model, we just say that if this person has recovered, then it has immunity, and it's like he could not spread the disease. Let us experiment with the same graph. We start with small number of initial nodes and get infection spray. So you say it's really dangerous situation. Half of the graph is almost infected. But next you have started recovery. So green are recovered nodes. And when infection spreads over the graph, so spreads recovered persons, because it's like they need to be ill for some time, but after that they get recovery and they get immunity for this disease. And next, you have another half of the graph almost all infected, but the previous part of the graph got recovered. So in this case, going further, we get all the graph recovered. Of course, not in all the cases the whole graph will be green, because in some cases susceptible persons will not be contacted by infected, and we may still have some persons who just remain in their susceptible case. So they still may be affected by infected persons, but they have no such opportunity. But for these cases, if the person was infected, then in some time period he will be recovered. And what about plots? I hope you see the colors. There are three colors. Green stands for recovered persons, red stands for infected persons, and blue stands for susceptible persons. And let us see in details about the first period. When an epidemic spread, we have increase of red vertices, we have increase of infected persons, and significant decrease of blue persons. So it means that we have people gotten infected. After that, we have some local maxima of the population of infected persons. And after this local maxima, recovery increases so much that infection dies over time. So it's like infection rate increased, and after that got decreased over time. So in this case, we say that epidemics occur if we have significant local maximal here. So in this model, we'll always have, when times tend to plus infinity, we'll have always having number of infected persons tending to 0. But we say that there exist epidemics if there exists this local maxima for which we have significant increase of nodes that represent infected persons. And let us show another example of simulation when we take small beta. In this case, infection immediately dies, because it's like infection spread was much slower than recovery rate. And in this case, we have a lot of vertices which are susceptible, so they are not, they have no immunity to this disease, but they have no opportunity to be infected. In this case, the number of infected persons just gets 0, and we have no spread of epidemics. And if we look on the chart, in this model, we have no epidemics, because you have no local maximal here. You have immediate decrease of number of infected persons. And although we have very small local maximal here, it starts decreasing from initial position. So it means it's like just the number of infection dies over time. In this case, everything is good, and we have still a lot of persons who will not even get sick once in their life. So, what about thresholds again? For epidemic thresholds, we have, again, the same or kind of similar relation. And we say that if infection over recovery rates fraction is greater than the epidemic threshold R0, then infection survives and became epidemic. And again, we call epidemics in SIR model the case for which we have significant local maxima, which is at least higher than the initial number of infected nodes in this model. So it means that usually when we have this epidemics of flu, we mean that we have some initial number of infected persons, and after that we have very high velocity of spread of infection. So it's like the population of infected persons increasing significantly in small number of time. So you see, it's really a small number of time to get to this local maxima. But to get infection cured, you need much more time. And this is what it's called epidemics, just in real disease spread and so on. If you have another situation for the second simulation when beta over gamma is less than R0 and less than epidemic threshold, infection dies over time. And we say that there is no epidemics because we have almost constantly decreasing function for infection rates and number of infection persons. So we just say that, okay, we have some initial infected persons, but our recovery is so good that infection just dies over time and the number of persons that got infected decreases. Yeah.
Blue and green line should be replaced because
yeah, I consider that's a mistake in the slide. So it's like here should be recovered green line, and here should be susceptible. Thank you. Just a typo. And it's kind of interesting to see that you have different networks. For example, it may be something like random network, lattice network, small world, special network, scale-free network, and so on. And for different networks, you'll have different type of disease spread because the network formation is really affecting the whole case of disease spread. Because, for example, when an infection gets to the vertex with high degree, next it will have probability to infect a lot of people. But if it dies, for example, or it goes to some small cluster, then it could infect small number of people, but it will be hard to get infection out of these clusters and so on. So it's really affected by the network formation. And one of your last homeworks, just not one, but just the last work, homework 4, will be devoted to studying the impact and differences of epidemic spread for SIR model between a real network and 3 random graph models that model this network. So you will need to think about how the network formation affects epidemics results and why it happens for different models in different way. So here is the representation. For random network, you'll have epidemics directly on initial steps, and after that, the number of infected persons will be decreasing over time slowly. For lattice network, when you have just lattice, it's the same as your mathematical notebooks. You'll have very slow time for epidemics, but it will be very long in the time because you will have slow increase until this local maximal. It will be not so much as in random networks, but after that it will be slow decreasing because you have just the same degrees for every vertex, and it means that it starts slowly spreading, and only then recovery rate try to get the same pace as infection rate. The thought is about small world. It's very interesting because it has a lot of fluctuations, and it's much closer to the lattice structure because it is based on the lattice graphs. But in some cases, epidemics may have much higher amplitude because in small world you have this connection rewiring things, and when this connection got used for infection spread, you could get from one infection part of the graph to another, and so the spread of disease may be much faster. And for spatial and scale-free network, you still have high epidemics in the first time steps, but their magnitude or the amplitude of number of infected population is a little bit less than for random network. What is about effective distance and so on? So just when you try to model infection spread, it may look in a very different way based on the graph structure that you have. Let us show in the first row. When you have some random graph, and you start with these red persons which got infected, and one of them got recovered, and you have this infection spread. So you may see that infection spread from green vertex to blue vertex may really take some time when this infection spread to this one. So it's like it starts increasing from green to their neighborhoods of their neighborhoods, and so on. So it's like it tried to fill the whole graph. But then it got recovered, and we removed just this, red indices indicating that the node is recovered. And in the end, infection dies over time. But when you get from one direction of the graph to another, it's like it needs really almost all the time when infection should spread through the whole graph to get to the vertex on the opposite side. So it means that going from this vertex to this one takes really a lot of time. So it's like you will need first spread some neighborhood of green vertex, and only then you will get to blue one. What about this structure? You have something like Cayley tree or tree structure of the graph, and infection was placed on initial position. And from this case, you could efficiently calculate on what step you will reach the blue vertex. It's something like you could calculate just the various distances for this type of the model and just estimate that this infection is really like a wave. When you, for example, when you just push some stone on the water, you will have these circles with increasing radius and so on. So in this case, infection spread from the central vertex to the next neighbors, and so on. And on each step, it just increases the distance from the original node. And at some point, it reaches blue, and after that, it just gets to the leaves of the graph, and after that, completely is eliminated from the graph. And another position, when you have started infection from some leaf, when you have a tree structure. And you could see that infection rate in this model is completely different. So it's something like it first tried to get to the center of the graph. And after, from the center of graph, it tried to spread further. And next thing, it again disappears. So it means that even having different initial position for these infected persons, you will have really different pictures of how these epidemics may work. So even understanding how to model epidemics, you'll still need some understanding of what is the most dangerous way, or it's like the most people who should be protected, so the epidemic spread will be as much less as possible. And if I'm discussing about social contagion, it's like social contagion phenomena refers to various processes that depend on individual propensity, and we try to measure how to adopt and diffuse knowledge, ideas, information, and so on. So in this way, when we first and originally talk about this, we could say that susceptible models is just individual who has not learned new information. While in the current state, we have our own beliefs, we have our technologies that we use, and so on. An infection rate is just a spread of information. So we have people which has different belief, different opinion, maybe different technologies. And recovered persons is just they are persons that are aware of information, but they are no longer spreading it. So I'm referring to recovered spread, for example, if we are talking about rumor. There is a constant yellow press which tells something like header that some celebrity dies. Yeah? And we just say, okay, we have a news that somebody died. And after that, we got infected because we may retweet, we may say to our friend, do you know he died recently? But after that, you get to Google and, for example, see that it was a rumor. It was a fake rumor. And usually many celebrities are striked with this rumor that just say that they died. And after that, you say, what the hell? It's like it's not possible. It's like we have another information that everything is okay and they're alive as always and everything is okay with them. And you stop spreading this rumor. You got recovered from it. It's very easy to understand when we are talking about social contagion in terms of just information spread. So recovering means we are aware of new information, but we are not spreading it. And two main questions, just if the rumor reaches high number of individuals, that's what happens when we have these orange revolutions, when we have something like epidemics based on rumor spread and so on. And another question is how to compute rate of infection spread, because when you have the social contagion, the rate of spread is individual for every person. So for some persons, the information may be relevant, for another not. And in this case, usually these rates are based off individual properties of a person who are spreading this information. And this is just example of meme diffusion on Twitter. So you'll have different results for different countries. So when we're talking about this memes diffusion, just the way how we process this diffusion of using these memes, it's really is affected by cultural dependencies, by the use of and structure of the network and so on. But you may see that this completely different structure, for example, when you have Japan graph, you have a lot of hubs or something like vertices which are important, and from them a large community immediately adopts it. But to go map from one community to another, it's very hard because they are not very good connected. For Syria, for example, you have another picture more like tree-like, when you have something like center of the graph and then it spreads further. But in some cases it appears to smaller communities, and inside communities you have much more spread than it usually has. So finally, some kind of, if you want to know about this kind of information propagation and epidemics outbreaks, you will have a lot of reference about this. So we have epidemic outbreaks in complex heterogeneous networks, and in general, the book about networks and epidemics model. And Secondly, it is very important to understand that we started a very new topic about dynamical process on complex networks. So it means that we have one network and it is fixed, but we could run different simulations. And even when we learn on classes how to simulate disease spread, for every kind of simulation we may have different results. And you will need to learn how to aggregate statistics from this process. And the same goes for dynamics of rumor spreading in complex network and some theory about this. So that's basically it. For if we want to learn how the information could be spread, then we'll learn the idea of how you could understand and how you could model this type of things. And usually you just use 3 parameters again. So we have some regional state, we have some new idea, new information, and we have the reflection of each person to this new information. In the SI model, new information just spread over all the network, and we could measure only its rate. In the SIS model, we just have this changing of information over time. So it's like we may reject this information later, then accept, and so on. And in SIR model, we just say that we'll have new information temporarily adopted, but then it will be discarded. So it's like it will be no longer spreading. So that's basically it. And if you have any questions, you may ask. If not, then we'll have consider short break, and then we could start classes maybe earlier. So we'll discuss how to make a modeling of this kind of epidemics, but in R. So how to program this type of things and how we could model them based on networks or just in whole process.